Okay, so the equation from the data, we get that the energy transfer is 0.625 distance squared. Okay? How about from the theoretical equation? From here it says it should be, and this time I'm going to write elastic because I'm trying to make this a law or a theoretical equation, right? You have 1/2 times my spring constant, which we already says 5/4, or 2.5, times d squared. Sorry, not 2.5. It's 1.25. 5/4, 1.25. So what is half of 1.25? Second time. Yeah, don't make it worse than it really is. Jeez. Okay, 0.5. Where's the light here? 0.5 times 1.25, right? That's this part. Boom. 0.625. It's still 0.625. D squared. Okay, so we get the same thing. We get the same thing. Whether you do it from the data or if you do it from theoretical, right? It all is connected. It all comes to the same conclusion. Therefore, the data verifies, or it's evidence for, this conclusion that the best fit, or the equation for the elastic energy stored in any Hookean spring. Okay, we've said Hookean springs is springs that behave like this. They're linear. Okay, a lot of stretchy things aren't necessarily like this. You can calculate it. Okay, it's kind of nice. You can calculate the energy. So let's generalize it. Force from a spring is K times the distance stretched. The elastic energy is 1/2 K times the distance stretched squared. And in general, this is quadratic. Just be very mindful about what your axes are showing. If it is a force versus distance graph, it's linear. If it is an energy versus distance graph, for springs, right? Okay, for springs, then it's quadratic. Okay? Questions on the outcomes here? Okay? You don't necessarily have to prove this or go through all the derivation steps. Okay? You're not going to be required to do that. But you should understand that we figured this out by looking at the areas under the graph, under these force versus distance graphs. Okay? That's a general concept that you do need to know. When you have a force versus distance graph, the work done, the energy transferred is the area under that. So let's put it into practice. How much elastic energy is there in a rubber band that has that much mass, that has a spring constant K equals 20 newtons per meter, and is stretched 0.8 meters? Okay, so the elastic energy is equal to 1/2 times the spring constant times the distance that it has stretched squared. The distance that is stretched squared. So, when you punch this all into a calculator, take my 0.5. Sorry, it's kind of hard to see. Can I? No, I can't. That's fine. Times 20. I'll just bring it like right up. It's so dark. It's so dark though. Like. Trying to see it? Okay. Times, parentheses, 0.8 squared. You see that? Equals 6.4. Okay, remember this is going to be in joules. The energy transferred is in joules. You have newtons per meter times a square meter. One of the meters cancel. You end up with newtons times meters. Newtons times meters is joules. Okay. This question can be a little tricky. This next one. If the rubber band is shot into the air, how high above where it was launched will it go? How can we relate the energy of this rubber band shot? Do I have a rubber band in here? I don't think I happen to have one. Oh, I do. It's already on the floor. Okay, so I take this rubber band, right? When I pull back, I store elastic energy. When I let go, and it hits my thumb. Right? Okay. It goes up to a certain height. Where did it get that energy to jump up? From the elastic energy. So if it had 6.4 joules of elastic energy, when it has launched and reaches the peak of its height, where did that energy go? When it is at the peak.
Stayed there.
Where? What? In what form of energy is that? Potential, gravitational potential energy, right? It goes from elastic, then it goes fast. All that elastic turns into kinetic. The kinetic drives it up, turns into potential, and then it falls back down, right? So, how much potential energy does it have when it reaches the peak? If it starts with 6.4 joules. It's still 6.4, right? If all of the elastic energy transforms into kinetic and then into potential, gravitational potential, you know, it couldn't have gone anywhere else, right? We're assuming it wasn't lost anywhere. So this 6.4 joules turns into 6.4 joules of gravitational potential energy. Gravitational potential energy is equal to mgh, right? So we can solve for how high it's going to go by solving for h in this equation, right? So it is 6.4 joules. Divide both sides by m and g. It tells us the mass is 0.1, g is 10. So we get, actually it happens to work out to be 6.4 meters. It just so happens to work out that way. Okay. But we can calculate how high it's going to go. If we can relate the spring potential energy to the gravitational potential energy, we can figure out how high things are going to go. Okay? Yeah, that's kind of hard to see. This is a 0.1. This is from the mass. And that is from g. Right? Because you're solving for h, so you just divide both sides. Okay. Questions? No. I want you to keep this for your notes. Okay. The last question says, if your friend did stretch her rubber band the same amount, but her rubber band spring constant was 10, explain why her rubber band would go higher or lower. What do you guys think? If her rubber band has a spring constant of 10, yours had a spring constant of 20, will her spring or her rubber band go higher or lower?
Lower.
Why? Why lower?
But isn't the more it is, the less it is stretching? Like if the hair's higher?
Well, it says if they stretch it the same amount. So it's the same distance stretched, but it has a smaller spring constant. Jace? I think.
I think it's it would be much lower because it has less constant.
Okay, so how does the less constant translate to a lower height? Oh, wait, harder to stretch? If it has a lower spring constant, does that make it easier to stretch or harder to stretch? Easier to stretch. So if it's easier to stretch, does it store more energy or less energy? Okay, it stores less energy, right? Because the E elastic is 1/2 kd squared. So if it's the same distance, but it's a lower k, you get less energy. In fact, she should have half as much elastic energy stored, which means that when it launches, it has less energy to start with. It will reach a height with half as much gravitational potential energy, which will mean it will get half the height. Does that make sense? Less K means less E elastic, which means less E gravitational, which means less H. Specifically in this case, because it's half. It's half, 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 half. Okay. Any questions about the worksheet? So this worksheet, there's a lot of, there's practice in it, but a lot of it's kind of notes too. So keep track of it. I want to show you guys kind of a neat video